Hello friends, after having completed block diagram representation and reduction, we begin with signal flow representation. Now what is signal flow representation? The signal flow graph represents a set of algebraic equations. For example, if you have x2 equals ax1, that means the input is x1, a and x2 such that the output x2 is a times x1, then it can be represented in this fashion. So I have the node x1 and then you have the second node x2 and you have a. So let us go through a few definitions. Now in any signal flow graph, what is a forward path? So a path connecting the input node and the output node is referred to as a forward path. Now while we travel from the input node to the output node, it is to be taken into consideration that no node is traced twice. So let's take an example. So let us consider an example considering the signal flow graph representation. Now let us consider this signal flow graph representation. Now here if I need to identify the forward path, I need to consider the path from the input node to the output node such that no node is traced twice. So if I consider the forward path P1, say I have G1, G2, G3, G4, G5. So this is the path. So I have G1, G2, G3, G4 and G6. Now there is another forward path P2 which is G1, G5 and G6. So I have G1, G5 and G6. Now can this be a forward path? Let's assume that I move in this way G1, G2, G3 minus H3, G4, G6. Now this cannot be considered as a forward path because I find that this node is traversed twice. So we have to take into consideration that when we move from the input node to the output node, no node should be traced more than once. So here for this signal flow representation, we find that there are only two forward paths, P1 and P2. And this represents the forward path gain. So how do we find the forward path gain? The product of the gains in the forward path represents the forward path gain. So I've taken the product of all the gains, isn't it? So P1 is G1 into G2 into G3 into G4 into G6. Whereas P2 is, you consider this forward path. So it is the product of G1, G5 and G6. So what is a loop? A loop is a closed path in the signal flow graph. Now let us try to identify what are the closed paths. So I find that G2 into minus H1. So there is one loop which is minus G2 H1. So this is one of the closed path. Next I have another loop L2 which is minus H3 and then L3 which is G4 into minus H2. So I'll write it as minus G4 H2. So these are the three loops and L1, L2, L3 form the loop gain. So these are three individual loops. So the next thing we need to find is non-touching loops. So two loops are considered to be non-touching if they do not share any common node. Now for example, I have L1 which is G2 into minus H1. So this is one loop. I have another loop here which is L2. Now these two do not share any common node. So L1, L2 are two non-touching loops. Now similarly I have L1 and L3 which is this loop. So L1 and L3 are non-touching loops, whereas what about L2 and L3? So they share a common node, so therefore these two are touching loops, right? So the non-touching loops would be L1, L2 and L1 and L3. So these are non-touching loops L1, L2 and L1, L3. Next we define the input node or the source node. So the input node or the source node is the node which has only outgoing branches, right? So the input node should have only outgoing branches and that is referred to as the input or the source node. Now similarly we have the output or the sink node. So likewise, the output or the sink node will only have incoming branches. Very simple. Now, in order to find the transfer function of a closed loop system, we use Mason's gain formula. So let us define what is Mason's gain formula, and we'll take an example and we'll see how we can find the transfer function of a closed loop system for a signal flow representation using Mason's gain formula. The overall transfer function of a closed loop system is given by Mason's gain formula, which is defined as the transfer function T of S is nothing but the output C of S by R of S input, which is summation K equals 1 to L Pk delta K by delta. So let us define what they are. Now what is L? L is number of forward paths. So here in this case there are 2 forward paths, so L becomes 2. Next you have Pk. Pk is the gain of the kth forward path. So this is the gain of the kth forward path. Now for example, P1 is the first forward path. So P1 is the gain of the path 1 and P2 is the gain of path 2, the forward path 2. And what is delta? Delta is determinant. So delta is the determinant of signal flow graph. Now what is that defined by? So please make a note. Delta is given by 1 minus sum of all possible combinations of loop gains. So you have sum of all possible combinations of loop gains, plus then you have sum of products of all possible combinations of non-touching loop gains, sum of all possible combinations of two non-touching loop gains. So I write LG for loop gains. Next, minus sum of all possible combinations of three non-touching loop gains, and it goes on, plus so on. Right? So how do you calculate delta? So that's going to be 1 minus sum of all combinations of loop gains. So that's going to be L1 plus L2 plus L3. So 1 minus plus sum of all combinations of two non-touching loop gains. So we find that there are two non-touching loop gains here, that is L1 L2 and L1 L3, minus sum of all possible combinations of three non-touching loop gains. So you do not have three non-touching loop gains here, and so on, it goes on. So this is delta. So we'll take a problem and we'll see how to find that. It will be much more clearer. And what is delta K? So delta K is value of delta not touching the kth forward path. So this value of delta, so this is the value of delta, right? 1 minus sum of all combinations of loop gains, such that it is the value of the same delta not touching the kth forward path. So if I want to calculate delta 1, I need to consider this where it is not touching the first forward path. If I calculate delta 2, I need to find the same value delta which is not touching the second forward path, and so on. Now how do we do that? How do we find delta 1, delta 2? How do we find delta? So let's take a problem and let's see how we can find these values. Find the forward paths 1, 2, identify the loop gains, 2, identify the non-touching loops, and also calculate delta and find delta K. So let's take a problem. So let us consider this signal flow graph representation, and we need to find the transfer function. So here we need to identify the number of forward paths. So that's the first job. So let's identify the first forward path. So very simple, I have G1 into G2 into G3 into G4, which forms the first forward path, such that no node is traced twice, isn't it? So all the nodes is being traced only once. So I have G1 into G2 into G3 and into G4. So then I have one more forward path, G1 into G6. So I have one more forward path, P2 equals G1 into G6. Next I have another forward path. I can go like this: G5, G3, G4. So then I have P3, which is G5, G3, G4. Then I have the fourth forward path. Can you identify the fourth forward path? So I have G5, then I have minus H2 and G6. So remember that none of the nodes are traced twice. So I go like this. So this node, and then I come back to this node and then go to the output. So remember, none of the nodes have to be traced twice. So you have to check all the options, right? So I have G5 into minus H2 into G6. So the first thing what we need to do is we need to identify the forward paths and get the forward path gains, right? So there are basically 4 forward paths, and these are the forward path gains. Next, we need to identify the individual loops. So how many individual loops are there? Let us try to identify. So an individual loop is nothing but a closed loop. So this is one loop, G2 into minus H2. So let me call this as L1 equals minus of G2 H2. Now can you identify any other loop? Yes, there is another loop which is minus H3. So let me call that as L2, which is minus H3. Now can you identify what are the other loops? So you have G2, G3, G4 and H1. See, G2, G3, G4 and H1. So this forms another loop. Let me call that as L3. G2 into G3 into G4 into minus H1. So this is L3. And what is another loop? So I have another loop here, isn't it? What is the other loop? G6 into minus H1. So this is another loop, individual loop. So I have L4, which is minus G6 H1. So I observe that there are 4 forward paths, and these are the forward path gains. I have 4 individual loops, and I have listed all the 4 loops. So next, what do we need to do? We need to find 2 non-touching loops. So how many loops are non-touching? So first of all, I find that this is L1 and this is L2. So these 2 are definitely non-touching. So I have L1, L2. So this is one non-touching loop. And is there any other loop which is non-touching? Of course, I have L3 here, and this is L4. So this is L2, sorry, this is L2 and L4. So I have L2 into L4. So L2 is minus H3 and this is L4. So these 2 are non-touching loops. Whereas all the other loops have a common node, right? So if I consider L1, so this is L1, and if I consider L3, of course they share common nodes. Then if I consider any other, for example, L1 and L4. So this is L1 and this is L4, they share this common node. So you find that there are only 2 non-touching loops. So after you find this, we find the determinant of the signal flow graph. I'll write signal flow graph, SFG in short form. So how do you do that? You need to calculate the determinant. So what does the determinant formula tell us? It is 1 minus all the loop gains, right? So that's going to be L1 plus L2 plus L3 plus L4. So I'll just write L1 plus L2 plus L3 plus L4 plus, so the sign alternates, into 2 non-touching loops. So this is one non-touching loop, that is L1 L2 plus L2 L4 minus 3 non-touching loops. So there are no 3 non-touching loops here, so that does not arise. So this stops here itself. So this is delta. Now apart from delta, we also need to calculate delta 1, 2, 3 and 4, because this value k represents the number of forward paths. So there are 4 forward paths. So I need to calculate delta 1, delta 2, delta 3 and delta 4. Right? So what is delta 1? Delta 1 equals 1 minus all the loops which do not touch the forward path 1. So this is the forward path 1. So we find that all the loops, individual loops, either L1, L3, L2 and L4, they definitely touch one of the nodes in the forward path. So it is 1 minus 0. So it is 1. Next, let me consider delta 2. Again I have 1 minus. Consider all the loops which do not touch P2. So what is P2? This is G1 into G3. So here I find that for G1, G3, L1, this is L1, isn't it? It shares a common node. L3 also shares a common node here. L4 also shares a common node. But whereas L2 does not share a common node with the forward path 2. So here I have 1 minus L2 plus 2 non-touching loops which do not touch the forward path 2 does not arise, so we stop here itself. Again delta 3 is 1 minus. So again consider the forward path 3, which is L5, L3, L4, right? So we find that all the loops L1, L2, L3, L4 will definitely touch one of the nodes of the forward path P3, so it's going to be 1 minus 0. And then what about delta 4? I have 1 minus. So this is the path, isn't it? G5 minus H2 G6. So G5 minus H2 G6, you have one loop which does not touch P4. Which is that loop which does not touch P4? Again I have this loop 2 here. So this is the path, isn't it? So this loop does not touch this forward path. So I have 1 minus of L2. Alright. So now what is the overall transfer function C of S by R of S? So what is the transfer function here? So I have P1 into delta 1, which is G1, G2, G3, G4 into delta 1 is 1. Plus P2 into delta 2. P2 is G1, G6 into delta 2. 1 minus L2. So I have 1 minus of minus plus. So I can write 1 plus H3. Right? Then you have plus P3 delta 3. What is P3? P3 is G5, G3, G4. Into delta 3 is 1, of course. P4 into delta 4. So P4 into delta 4. P4 is this expression, which is, I'll take a minus sign here, G5, G6 into H2 into delta 4. So what is delta 4? 1 minus L2. So I can write it as 1 plus H3 into 1 plus H3. So this whole thing divided by delta. So let's write the value of delta. So delta is 1 minus L1 plus L2 plus L3 plus L4. Now all these values are negative, isn't it? The loop gains. So if I remove the brackets, they become positive. So I'll write plus G2 H2 plus H3 plus G2 G3 G4 H1 plus G6 H1 plus, so I have L1 L2. So when I multiply these two, it becomes positive. So I have G2 H2 H3 plus L2 L4. So I have G6 H1 H3. So this is the final transfer function which we have obtained by using Mason's gain formula. So in this video segment we have gone through Mason's gain formula. We have defined how to find the transfer function using Mason's gain formula, and we have taken an example and we have obtained the final transfer function. In the next few video segments, we will solve some more problems to find the transfer function using Mason's gain formula. So do not forget to view all the other videos and practice problems. And also watch the other videos in control systems. All the videos have been placed under the playlist control systems. So do not forget to like, share and subscribe and view all the other videos and solve problems. And thanks for watching.